All right, thank you so much. Can you just confirm that you can hear me and see my screen here?
Yep, looks good. Sounds
All
good.
right, cool. Well, thanks everyone for joining. As I was watching people log on, I recognized some familiar names, so I appreciate that. It's always fun to see those people. So thanks for joining. Yeah, today I want to talk about advanced computation in lighting and daylighting design. My name is Reinhardt. I've been with Smith Group for about 8 years now. I'm a lighting designer by trade, but I also do a lot of daylighting work. And more, I'm doing a lot of computational work, both for lighting and daylighting. And so becoming really interested in what our machines can do for us in our process and how we design. And so that's what I want to talk about today and why I think it's important. I'll probably spend about 20 minutes talking about this, and then hopefully we get some good questions and conversation going. So for the learning objectives, basically what I said earlier, needs and advantages of advanced computational workflows. I think they're sort of the way of the future in a lot of ways in what we do as lighting designers. And I'm just sharing a couple case studies of how we've done that. I want to identify and sort of drive home why we as the designers, the lighting designers in particular, play a key role in computationally intensive processes moving forward. Understand the challenges and opportunities in adopting these workflows, and then finally understand the takeaway, which is sort of to model your project specific challenge or script your challenge, and then inform the design. So as I was researching for this topic, I've talked about this topic a couple times now, I think 2 or 3 times at other forums. I always come back to this in Thomas Kuhn's idea of the paradigm shift. So in his work, The Structure of Scientific Revolutions, he outlines the difference between normal work and extraordinary work. And without getting too deep into the weeds of it, essentially there's enough external pressures on our industry, whether environmental or societal or just project complexities, that warrants a different way of working. And I think that we have already entered that new paradigm, and I think it's largely computationally driven. If not already, some of the stuff I've shown today is actually quite old compared to the rate of which things are advancing with AI. But that's a whole conversation we get into moving forward. So anyways, I think this sets the groundwork nicely because I think we are in a fundamentally different way of working and engaging with our design processes. So I like this chart here because it sort of outlines where we want to be and how things build on each other. So if you think about data, or if I say 55, that doesn't really mean much. If I say an SDA, a spatial daylight autonomy of 55, well, that's a piece of information. Now that's useful and we can start to use it. Mr. Alistair McFarland defined these terms nicely, I think, in 2013. He said that information describes, so right, that tells us what the world is today, or world is now. Knowledge prescribes, it tells us what to do in circumstances that we may have encountered before, our accumulated experiences. Intelligence decides. That's a way of working that tells us what to do or guides us in situations that we may not have experienced before. Right, so there's slight differences in how you define these terms. And I would, as the designer, urge us to be working in the knowledge and intelligence areas as often as we can. And I think that's kind of the change in the perspective here. And so that's what I want to show today. If you think about the traditional validation process, right? Oftentimes we get a building from an architect and they tell me, tell me how good I'm doing. And then we run an analysis. While there is use in that, it doesn't really inform the architecture as much as it could, right? To tell them that you have a glare problem, the very next question is, okay, well, then what, right? So the better way of working, our ideal sort of workflow here would be to flip the script. If you can do the analysis beforehand, or ideally at least at the same time that major decisions are being made. This is actively what we're working on to try to do more and more of, and there's more theory behind all this that we can get into, but you use this analysis to then inform the design decision. An easy way to think about that is orientation massing programming for the architectural building, right? That's a very concrete example, but it can apply to lots of different disciplines and ways of working. To do this successfully, I think you have to think computationally. And so Leland Curtis, former colleague of ours, kind of broke down what we think the stages are of computational thinking. And they kind of go like this: stage 1, 2, 3, and 4. And as you move to the right, they get more complicated, right? And we're going to touch on what each of these are and show an example. So stage 1, a parametric model. That's the most basic thing you can do, which is to basically speed up your existing workflow. If you think about the fact that we have a design We then model that design in our software and then calculate it. I always go back to daylighting, but that's just the example I'll use. You can apply it to different disciplines. You then analyze your data and then you provide feedback to the team. It's not until that purple pink arrow that we actually add value to the project. And so yeah, the idea here is that you do this faster and more often. So that could look something like this, right? So this is our T3 project. We just parametrically built this skylight within an existing structural bay so that we can model the daylight effect inside the concourse. By manipulating the structure in that way, just geometry, we're able to iterate through more daylighting options quicker. The next step in this is stage 2, parametric engines. These essentially act as a way to automate your workflows. So now what we're doing is we're packaging your parametric engine, your model, your calculation, and your analysis engine at the front end, and you can run through more options, more purple arrows to inform the design. That's the basic premise of a parametric engine to automate those workflows. So what does that look like? This is our University of Michigan BSB project a few years ago, where we created a room here that iterated through different possible combinations of vertical baguettes and terracotta baguettes. And we essentially created a menu for our architects that said, here are your possible solutions, or how we think the solutions are, and the impact to the interior daylight, in this case, daylight autonomy. So what they were able to do is take an aesthetic stance and look at the building, how they want it to look like from the outside, with the information needed for good daylighting on the inside of the building. And so this is a pretty unique, I think a pretty strong way of working with our architects, not so much dictating the design, but certainly informing and adding some energy and data and daylighting data to the decisions that they make. It starts to get really interesting in stage 3, iterative modeling workflows. So we just talked about a parametric engine. All the sort of boxes you see on the bottom there are different ways of employing and running a parametric engine. We won't go into the details too much of these, but the ideal way of working on this would be a universal design space, sort of the far right there. There's just a paper published by my colleagues Stett and Leland Curtis and a couple other folks that outline universal design spaces as it relates to energy modeling. You should definitely check that out. I can share the link later, but it talks exactly about this type of thing. So we'll talk about what the design space is here in just a moment, right? So a parametric workflow, though, very generally is something like this. This is the Grasshopper script, which is a visual scripting platform. Essentially, if you look at the far left, we have parameters 1 and 2, right? We're just looking at A, B, C, X, Y, Z. And we're combining those parameters within this visual scripting program. In this case, Calibri is the module. And we're going to tell it to run through each combination of those parameters. So you see AY, AZ, etc. We record all of those possible combinations, in this case, a CSV file, that gives us the output of the combination and the input parameters. Now imagine that we were able to do this with way more complicated parameters and actually attribute data to it, whether it's daylighting, energy, lighting design, whatever data you're interested in, you run through this sort of iteration process. When you're starting to do that way of working, you're creating what we're calling the design space. What you're doing is you're modeling all of your design decisions. Ideally, in a sort of utopian world, we've modeled all of the gamut of possible solutions. You've simulated all those different iterations, and then you look at the data. You use data trends and data science to understand the trends in performance. You then take those takeaways and you inform the design process. So the workflow here is model your design decisions, simulate your iterations. Each one of these dots represents a possible solution, and use your data to analyze and then inform the design. So this is a parametric model. We're changing the glass width, the facade depth, and the ceiling height, right? This is useful geometry play. It speeds up our workflow. You then run through all of your combinations or your design space as a designer. You set those up and you get something like this. So imagine, if you will, we change the window width on one axis, the fin depth in the Y, and the ceiling height in the Z. Each one of those different combinations is an option. And when you plot those options in this parallel coordinate chart, you have a bunch of different metrics that you're tracking. So you may have seen the spaghetti junction before. That's essentially what's happening. Each one of these lines represents a possible combination that has associated inputs and associated outputs. And what we're trying to do is map the design space in a way that we can track the trends throughout. So that's what Design Explorer is doing. If you've ever used this tool, quite a cool way of working. So what does this look like in practice? We have two projects here. The first is a daylighting project. This is a lab building with our San Francisco office. And what's cool about this project is they brought us on board very early on to help design this unitized panel system. They have an aesthetic that they're going for, but they were curious how they would perform from a daylighting and energy perspective. And so the team had several design decisions. One was the transparency of the different glazing units, the size of the glazing, the window to wall ratios, as well as the horizontal terracotta baguette spacing, depth, just the arrangement of that passive design strategy. Those facade units could then be multiplied across the facade at all different orientations to create a certain aesthetic look and function to the building. So we were brought on board to help analyze the daylighting and energy. This is a perfect example of using design space exploration. You model the challenge, you generate your options or your solutions or your space, better yet, and then explore the trends in the data. To do this effectively, I think it really does take sort of four things. And conveniently, I think they start in T, so timing, teaming, tools, and talent. So if you think about timing, the best time to do this is at the very, very early on in the project when the impact is highest, decisions are being made architecturally, and the cost is relatively low to change something. So that's the ideal way of working, right? In this project, we were brought on board early. Teaming is understanding that a lot of these decisions that we make impact other disciplines. So as a lighting designer, I very strongly understand that daylighting is very closely linked to solar load, heat gain, electric light savings, right? Things that energy modelers are concerned about, or building techs. At the end of the day, everyone is sort of concerned about energy use intensity, as they should be. And so we play a small part in a much larger picture, but recognize the integration that's required in this way of working. The other part of this is tools. So if we talk about how we built this, if the model's on the far left there, we look at a typical floor. We've created the forms and the parameters within this visual script. The script you see on the right is a snip of the computer screen of the Grasshopper interface. The first bucket is form creation and geometry to build the model that you see on the left. The second bucket is our analysis engine. So in this case, we have energy and daylighting. And then on the third, the far right, we have an iteration section that essentially will iterate through all of your combinations, run it through your analysis engine, and record the data. And so we're taking our model, here's a snippet of that on the left, with our unitized facade panel. We're running it through Climate Studio for daylighting. In this case, we want to increase spatial daylight autonomy and useful daylight illuminance while lowering ASE. At the same time, we're looking at Energy Plus, and I worked here with Jake Chevier from Smith Group and our performance analytics team as he ran the energy model. And we wanted to decrease, in this case, peak cooling for this lab building, and that's the metric we were concerned about. As you can recognize, oftentimes these variables are competing. While I want to increase daylight, he wants to decrease the peak cooling due to solar load. And so we have competing variables. There's a compromise in our design. And so we're taking this parametric model, we're running it through engines that we know and trust. Climate Studio gives us, SDA, DA, UDI, all the typical metrics we as designers are used to. And then Energy Plus is, in this case, showing a load balance, but we can, fine tune it for peak cooling or at whatever we want to. And so we're running it through trusted analysis engines and using these parameters as our inputs. So the design decisions drive the parameters. At the top left is facade parameters, so different window to wall ratios, whether it's punched window or ribbon window. Layered on top of that, different shading parameters, so horizontal baguettes and overhangs. You get a graphic that looks like the right. This is looking at just the south facade, for instance. Each one of these lines represents a possible combination, and you can see how this visually builds a design space that is sort of hard to visualize. But what we do is we run through all of those different iterations for each of the facades, the west, the south, the east, and the north. And it's interesting how the behavior of these change depending on the facade, which is exactly what we wanted to see, meaning that the daylight energy could change the way that fins respond based on its orientation. So if we look at the south facade, for instance, what I've done here is I've plotted the mean UDI. So at the bottom there, useful daylight illuminance average on the bottom, peak cooling on the y-axis. And each one of these dots represents a possible solution that we've iterated through. And all we're concerned about is what is the major trend. And so we've created here a Pareto front. There are more optimal solutions and less optimal solutions. As you work your way to the right, there's more optimal solutions. And what we could do is start to bucket down the solutions that we want to show to our architects. So if our goal is to at least have an SDA of 55, in this case, I'm using LEED as our objective metric, 55%, and reduce our peak cooling by 5%, which our energy modeling team agreed would have an impact on the mechanical systems, we filter down our 292 options to 26 options. So in a way, what we're doing is we're not saying this is the best solution, but we can go to the architects and we can create buckets of different design decisions that they can then apply for other reasons, aesthetics, cost, maintenance, etc. Now backed by useful daylight and useful energy analysis. And so we've created these buckets that you see here, not recommended, for instance. So don't do a combination of these parameters, or at least we would not recommend it. The daylighting is too low. You could do better by using these parameters, 3-to-1 spacing on the baguette spacing, 3-to-1 spacing to depth ratio. You could do the best by increasing your daylighting while maintaining the peak cooling impact. And so we've created these buckets so that we can better inform the design team as they move forward. What's cool about this way of working is informed design, meaning that we work in Rhino, where the architect was working, using Grasshopper, Honeybee, Ladybug, and Power BI to analyze our data. In the future, we're looking to use evolutionary solvers for multi-objective optimization to sort of even get a bigger span of possible solutions, ongoing research, which didn't make time for it, and using surrogate modeling. That universal design space paper I mentioned uses this method of surrogate modeling to sort of use a practical machine learning to gather our solutions. We're also creating interactive deliverables so we can share this with our designers so they can go on a website or app and run through their room, for instance, and get a good sense of how the daylighting is doing or the energy is doing for that particular program. And I'll quickly shift here to a lighting design example. So this is the Pinecone Sky Tower in Gatlinburg, Tennessee. Really cool project. This is sort of pavilion outside up on the hill. And you walk around, you see this tower, and this tower is clad in metal panels. It's quite beautiful, just sort of as you walk around it in the perspective. It creates a lot of challenges for us as lighting designers to illuminate this tower. Conceptually, this tower represents a pine cone that in this region, when there's wildfires, is actually sort of unravels and regerminates. So the idea here is that this tower represents this rationalization and the rebirth of the wildfire that impacted the area recently. The challenge for us is that the material is difficult to model. It's an anisotrophic material at a micro level. The light behaves very differently as soon as you rotate it just a little bit, as you can see here. You can imagine that if you scale this up to the size of the tower, you have a bunch of different viewing angles, a bunch of different lighting locations. It is quite the challenge to model this. And so here we wanted to explore how to do it effectively in the virtual environment to predict the actual lighting output photorealistically and photo accurately. So what we did is we did a quick mock-up. We took a panel, 6" by 8" of what's proposed. We put it on a board and we rotate that board around at different angles. We lit it with the proposed light fixture at a certain distance and moved that around as well as the camera. We took measurements of both illuminance and luminance for each of these different locations and rotations, right? So we're building a big data set in the real world of luminance and illuminance as all these different sort of possible combinations that you can see here. You can build that out into an Excel sheet, right? So we're using data and information to kind of guide our design decisions. And you can start to track here on the left is a Photoshop image of all the metal panels sort of moved around that board. Just note that as you look at the luminance, for instance, at the top left, that low value luminance has the highest illuminance, which corresponds to the image that you see on the left and sort of reemphasizes the point that this metal is strange, as we know as lighting designers, hard to illuminate. And so we use this data to basically inform our 3ds Max material that we typically use for running our lighting simulations and created the rendering on the right that we feel pretty good about because it was validated in the real world. However, we thought we could do better and actually wanted to create a parametric way so that when the tower gets updated architecturally, our lighting design can get updated. And so we changed and started to use Grasshopper, Honeybee, and Ladybug through a radiance engine that produced the rendering on the far bottom right there. And so what's cool about this process is that the architecture team built the entire model in Grasshopper. That's the blue box that you see there. We went in and defined our IES photometry in Grasshopper as well, linked to the architectural geometry and ran that through a radiance material and calculation engine. The idea here is when architecture changes, and they did change the architecture, our lighting design automatically changed as well, or was closely tied to. Imagine replacing all those IES files as slight panels shift. How annoying that would be. But this sped up that workflow incredibly, and we were able to re-render quickly. And so basically we have the mock-up luminance readings on the far left. What we did is we sent the material into a radiance module, right? We're familiar with radiance materials. We defined the roughness and specularity. What we did though is instead of having a poor intern slide that ruler that you see there, which is different values of roughness and specularity, we used Galapagos, which is sort of an evolutionary solver, to iterate through the possible combinations of roughness and specularity to, as closely as possible, match our mock-up luminance readings when you apply radiance material and the IES photometry. So what we used is we use that evolutionary solver to get us 99% of the way there. And then we open up the model the next morning, we fine tweaked the inputs, and we got a material that behaved the way that the actual physical world material behaved, which was quite cool. That led us to renderings that you start to see here, much more representative of what we feel that metal was actually doing on the mockup, based on the radiance iteration that we built. And now we can use this for luminance readings, illuminance readings, etc., to design, right? As designers, we want to design. And so you could floodlight the building, you can integrate LED accent lights within each of the panels, and we ultimately ended up with a combination of the two, flood and panel, that you see at the far right there. And so we started with the rendering on the far left. We ended with the rendering that you see on the far right, which we feel represents the material well and is built on this parametric workflow, which is just a really cool way of, I think, achieving a pretty complicated problem. So last but not least, my key observations in this way of working is that it takes tools, teaming, and timing. Talent, I think, is the last one. You want to leverage projects when possible. You're not going to be able to do a lot of these things all at once, but little bits at a time really build up over time. Break down your problem and script the challenge. Think about what you're actually trying to address and build your script around that, those parameters. Understand and communicate your constraints to not only yourself, but to your team. What is the data telling you, but also what is the data not telling you? I think as this way of working becomes more popular, we as designers need to understand the methods of machine learning and data science a little bit more. Build and use your resources. So partner with others that know how to do this stuff. It's going to make things much easier. Document the process as you work through these things so that you can share out these ways of working and share knowledge effectively within your firm and with other people. I think part of the reason this is such a beautiful thing is that a lot of it is open source. People much smarter than I are developing these modules and these workflows that you can implement into your own day-to-day doings. With that, I'll pause for any questions. I think we have a few minutes left. So just wanted to thank everyone again and let me know if you have any questions. Not sure if there's any in the chat. Oh, we do have one in the chat. Okay, first question says, great examples of how data and parametrics can support design in an impactful way without sacrificing the aesthetic vision. What would you say is the most exciting thing about these ever-evolving processes and biggest challenge? I think the exciting thing is that I think this is becoming more and more popular, and I don't want to say expected, but I think a lot of architects are starting to work this way if they haven't already. I also think it's just what's going to need to happen. We're going to be encouraged to be designing sustainable buildings and meet the goals that we set for ourselves. This way of working to help, I don't want to say optimize, but to help set our projects up for success early on in the project when this major design decisions are made, I think is a big challenge. It's difficult to get people on board sometimes and to implement some of these things. But it's also probably one of the more important things that we as designers can be doing in helping our design teams set up for success. Biggest challenge, the learning curve is a bit steep. The good news is there's lots of resources on this online. It takes time, it takes practice and a lot of patience. But it is a little bit different because you're thinking differently. The good news is for me personally, Grasshopper and Dynamo are visual scripts, and as visual people, it makes the process a bit more fun and interesting to work on. Where did you get started with learning tools? Yeah, all right, so there's a good follow-up question. In this case, it was back in 2014 is when we first started working on this. Back then, we just had YouTube tutorials for the few people that were doing it and blogs. So Grasshopper, Rhino community, that community is really strong. So Ladybug, Honeybee, those analysis tools have forums where people are always posting every day different problems that they're running into or different workflows that they see are working and not working. So that's one really good resource. There are tutorials online via some of the Grasshopper forums that give you the basics of parametric design. So just how models work, like how to add two numbers, how to draw a line, and they kind of build on each other. And then there are several YouTube videos by some of the people that develop these tools. Mustafa comes to mind, for instance. If you just go to YouTube and maybe search, basics of Grasshopper, a lot of times there are playlists that people have built you that will take you from the beginning of building a simple box to the very complicated building a crazy facade that responds to some sort of like line that you draw in Rhino. So the good news is lots of people have put resources out there. The best way I've learned is just trial and error, using YouTube, and then reaching out on forums and asking for people for help when I get stuck. Any other questions? I don't see any other questions in the chat. I don't know if you can unmute yourself, but I think we have a minute here.
All right. Well, thanks everyone for tuning in. Again, this recording will be uploaded. Certainly, if anyone thinks of any questions afterwards, feel free to send them over to iesrmsdenver@gmail.com. We'll get them over to Reinhardt and can get you an answer. Stay tuned for more of these in the future. The goal is to do these monthly. So there will be more announcements coming soon. Thanks, everyone.
Thanks all. Appreciate it.